mics while the meeting gets going.
So good. Thanks so much, Chris. Chris is our behind the scenes guru today. He's handling all of the good techie stuff that makes this happen. So stuff that's far beyond my skills and abilities. So a big thank you goes out to Chris for doing that. And nice to see all of you here tonight. Welcome. This is the October meeting of the Hamilton Amateur Astronomers. We have a great guest speaker today. We have some wonderful door prizes. We have the sky this month. And for those troopers that stick around to the end, we have the introduction of our new council. And to entice you to stick around to the end, we've got our regular 3 door prizes, and I'm going to throw in an extra one right at the end for anybody who sticks around for the boring business stuff. So and speaking of the business stuff, don't forget that this is the time to renew your membership. This can be done easily online on our website since we're not there in person these days. Membership for an individual is $40 and for a family it's $45. And this is a fantastic bargain if I say so myself. So now's the time. So if you have any questions, you can get in touch with our treasurer, Andy Catch. treasurer@amateurastronomy.org. But now's the time to do that and get all signed up for another year. I, of course, am John Govro. I am the chair. I get to say that today. I'm the chair of the Hamilton Amateur Astronomers. And a big welcome to all of you for joining us this evening. Oh, you know what I'm going to mention? I'm going to mention throw one other little tidbit in here, just because I haven't seen it yet. But the November issue of Sky News has a write-up on Carrie Ann Leckie Hepburn, a long ago member of the HAA and a friend to many of you. So when I can get my hands on a copy of that, I will be, I'm looking forward to that. That's going to be in the November issue. The Telescope Loaner program is back up and running. And you can, if that's something that interests you, you can reach out to loanerscope@amateurastronomy.org. And we have a stable of telescopes that are available for our members to borrow for free, and there's some other interesting tidbits in there as well. Some telescope accessories, eyepieces, a Malin cam, all kinds of interesting stuff. So there is that. That is up and running. Again, I'm very, very happy to say, and other fun stuff. So so as we wrap up this membership year and head into the next one, everything seems to be going very, very well at the moment. I'm very happy to say. But tonight is all about our guest speaker. So we have a very special guest speaker today. It's Laurie Rousseau-Nepton. She's an astronomer in residence at the Canada-France-Hawaii Telescope at Mauna Kea in Hawaii, and was a postdoc researcher at the University of Hawaii from 17 to 19. Dr. Rousseau-Nepton is the first Indigenous woman in Canada, I think, to obtain a PhD in astrophysics. She can correct me if I'm wrong. Got her diploma from the Université Laval by studying regions of stellar formation in spiral galaxies. She was an FRQNT postdoc scholarship recipient. Previously received the Hubert Reeves Fellowship and the Award for Native Women in Sciences. She is involved in equity, diversity, and inclusion committees for the Canadian Association of Physicists and for the Mauna Kea Observatories, and is devoted to promoting a community-driven way to do science. Right now, Dr. Rousseau-Nepton is the principal investigator for SIGNALS, the Star Formation, Ionized Gas, and Nebular Abundances Legacy Survey, a very ambitious project, which is exploring 50,000, give or take, star-forming regions in nearby galaxies. It is the largest and most comprehensive database of these regions that has ever been put together. If we were there in person, and Dr. Rousseau-Nepton had the opportunity to be here to see us, we would give you a big round of applause to welcome you here. but you'll take my word for it that that applause is there in our minds, and I'm very, very happy to turn the floor over to you now. Welcome.
Thank you so much. It's a pleasure to be with all of you guys today. It's a little bit earlier for me in Hawaii. It's just 30 minutes past my lunchtime. And so I have a presentation for you guys today that's going to cover a lot of different things. And I build it in a way that it leads to signals. So of course, my science is about signals. I want to share with you why I love this project, and I think it's going to really bring new science. And obviously, I wish it's going to increase our knowledge on how stars are forming and how this process of star formation is super important on our understanding of the universe. So my presentation is going to go across the telescope here that I work for, the Canada-France-Hawaii telescope. I hope some of you are familiar with it. I'm going to introduce a little bit the science topic, star formation. I'm sure you've probably heard about it many times, but you're going to hear from it from my point of view. And we're going to talk about instrumentation a little bit, because I use instruments here at the Canada-France-Hawaii telescope that are ideal to do surveys like signals. So I'm going to show you how they work, how CITEL, the instrument that I use, work. And hopefully you'll be able to appreciate how ingenious it is. And it's an instrument that has been built in Canada, so we have to be proud of it. And during the introduction, there was a mention about community science. And I like to talk a little bit about that as well. It's a little bit what I'm doing today, talking with you guys. It is very important for me as a scientist to share what I do and explain it to the public at every level. And I think it is important that every scientist, no matter where they are and what they do, take some of their time to do that. Because at the end of the day, we are trying to increase the knowledge of everybody, not just ourselves. So to me, it's really, really important. And in doing so, we're also trying to build project with the community in doing science and making it more digestible for everybody and more fun. So you're always welcome to contact me if ever you have any ideas about that. So I'm going to start sharing my screen. Hopefully it's all going to work on the first attempt.
Like this too, don't you? Got it? Got it? Just reading.
Is it working? I cannot see anybody. I'll just assume it's working.
Yes, it's working great. I see it perfectly. Thank you.
Awesome. Perfect. So the first few images is just to talk a little bit of where I'm from. So I'm from Quebec, the Quebec province. I am also a member of the Innu Nation. And this image is from Laval University, where I did most of my study, baccalaureate to PhD. And you can probably notice I'm right there in the middle of this group. We were also collaborating a lot with all the universities across Quebec, actually Montreal, Bishop, and McGill, and others. And all of these universities have different groups doing different science. And I was within a group at Laval that was driven by a project to build an instrument. And I spent a lot of time at Mont Mégantic Observatory, which is perfect to learn to use a telescope. And they have a lot of instruments there. And back then, I was also training other students to use the telescope and the different instrument that we had. So I got the pleasure to work with infrared and visible camera and also spectrographs, and including the very one I used for my thesis, which is Espion. It's a Fourier transform imaging spectrograph. It was built by the team of Laurent Drissen and other students. And I was under the direction of actually his wife, Carmel Robert, who was my supervisor for my PhD. And Espion is right there on the telescope. You can see it here. And it was the precursor of the instrument I use now, CITEL, the Canada-France-Hawaii telescope. So spending those years at the Mont Mégantic was really helpful for me. And part of my job was to show that the prototype Espion was working and that we could do great science with it. And it was absolutely essential because we needed funding to build a new version of it, CITEL. And fortunately, it worked. So all the analysis that I did back then on galaxies revealed that Espion was totally capable of doing great science, and we got some funding to build CITEL. And it took years. It started in 2010. I was starting my PhD back then. We built CITEL from, like the model of Espion, but it was meant to be installed here in Hawaii on a larger telescope. And also here we work at the Canada France Hawaii, we work remotely. We're not at the summit. The Mauna Kea is a very high mountain, so we don't want to have the high altitude symptoms or, the high altitude sickness you can have while working here. So everything in the instrument had to be.
They actually found the water.
Is there a question?
Hey, sorry, whoever has their microphones on, can they please mute them, please?
Okay. So we really needed the instrument to be able to work completely remotely without any human intervention. So we built it differently. And that image that I'm showing you here is all the group that actually followed the instrument after the delivery in Hawaii. And we were in the control room, waiting for the first leg to come into the instrument. It was very exciting. That week, we only had 7 days to do all of our observation and our tests to prove that CITEL was working well. And we had a hurricane that was literally going directly towards the islands. And fortunately for us, Guillermo decided to go completely north at the very last minute. And we got 7 days of full clear sky, perfect photometric condition for testing CITEL. And one of the first objects we observed was a planetary nebulae. This is one of the first images. Doesn't look super good, but once the data were analyzed and we could make pretty images with it, this is what the planetary nebula looked like. But me sitting in the back there, I was actually more interested in that small galaxy in the background. And very quickly, I could analyze it and show that we could study both the chemical composition of the galaxy using the spectroscopy of the data, and also measure the velocity curves of the galaxy. So the dynamic part of the analysis. And it was really exciting. Everybody was just super proud that all of this project was, at work on the first attempt. And after all those years of work, it was really a good reward to see the first data getting in. And I finished my PhD and got hired here as a resident astronomer. So I followed the instrument with the expertise that I have in Fourier transform spectroscopy. I now help a lot of people around the world to use the instrument. And if you've never been to Hawaii, so the Big Island of Hawaii is the largest island of the archipelago. There's large mountains here. They're all volcanoes. And fortunately, the one where our telescope is on is not active. So the Mauna Kea is on the northern part of the island right here. On the oldest part of the island, Mauna Kea has not been active since about almost 6,000 years. And the active part of the island is actually further south, where you have the Mauna Loa and the Kilauea volcano that are often erupting, to a time scale of volcanoes. And we have to deal with that. So here we have fog, so the smoke coming from the volcano, and we have earthquakes quite often. And this is something that we have to deal with at the observatory constantly to protect the instrument, but also the mirror of the telescope. So the fog, the volcano smoke is acidic, and at night, if it reaches the higher up layer of the atmosphere, it can reach the mirror, and it's actually degrading the mirror quality. So we have detectors to detect that and close the dome if ever it happens. The volcano is currently erupting. The Kilauea started erupting again last week. So this is an image of the eruption at the beginning. So you see the date here. This was September 29th. And fortunately, it's erupting just in the crater. So it's pretty far away from the Mauna Kea. And it's mostly blocked by the Mauna Loa, another mountain in between that is pretty high. So we don't get too much VUG currently at the summit. And if you've been on the island, you might remember seeing the Mauna Kea. We see it from most of the areas on the island, and it's a very large mountain. It's 4.2 kilometer high, and we do have snow during the winter months. And you can see on the summit, the telescope, the Canada-France is this one on the left. And depending on the season, you might see it also like this. This is a view from the other side on the Mauna Loa. And there's an access road that goes all the way to the summit. And once you reach the summit via that little road over here, you'll see multiple telescopes that are in the science reserve. So this is an image that shows all the telescope in the science reserve close to the summit. And this one right here on the center is the Canada-France-Hawaii telescope. So I'm going to show you, one last video of some extreme weather we can have sometimes here. So this is a video showing lightning striking the Gemini dome, and Gemini is our closest neighbor on the mountain. And those lightnings actually, since we're connected to the Gemini telescope with a fiber optic in a metal pipe, actually, that a conduit that leads the fiber optic to our telescope, we actually had damage in our own systems because of that lightning strike. So yeah, we really have to deal with a lot of things here that normally don't happen in most telescopes. But it's totally worth it because most of the time you're above the clouds and you have exquisite image quality. The sky is photometric and it's beautiful in the Mauna Kea. And even without using any adaptive optics system or a system that helps improving the quality of the images, we can get quality of image that ranges from 0.3 to 0.4 arcsecond without any extra work, which is amazing when you compare with what you can get normally at Montmagnetic Observatory or in a small observatory elsewhere in Canada. And this is our dome with the vents open. And I think the next one is going to be inside. Yes. So now this is inside the dome, and we have a view from above the telescope or on the side here, so you can have an idea of the dimension of the thing. And now I have a video that will show you how everything works, how everything moves. So as soon as the sun is setting, we can open the slit to let the cold air get inside. I wish I had sound on this video because there's a lot of, it's really noisy when all of this happens. And it's super impressive to be actually in the dome when all of this happens. You're gonna also see the dome vents opening and eventually the dome rotating, and also the telescope moving. And we work here with about 50 employees. So for that to be able to happen every night without any technical issue, and also optimizing the quality of the data, we need everybody. We have teams at the summit during the day that make sure that all the building systems are working fine. We have engineers that also monitors our cameras and instruments. And we have also software and database specialists that deal with the flow of data coming from the telescope. And me as an astronomer here, I help planning the observation. I help distributing the data to everyone around the world that have asked for data from our telescope. And I also help them analyze the data themselves and do science, of course. So today we're going to talk about star formation, which is my the part in the field of astrophysics where I'm specialized in. And it is important to understand why star formation is so important in a global context of understanding our universe. So I'm not going to go in great details in explaining the theory of the Big Bang because I'm sure all of you know about it. But since the Big Bang, the universe has changed a lot. The structures formed, the first stars starting to shine after about 300 million years. And then all the galaxies formed slowly, and then forming different forms of galaxy, smaller and merging together, forming larger galaxies, and eventually the galaxy that we know today in the local universe, with all the different shapes that we are used to, of course, the spiral, the irregular and elliptical galaxy, and so on. But the stars have been forming in the different periods in the universe And they have been transforming the universe significantly, and they're still transforming the universe today. So it's absolutely essential to understand the physical processes that are involved in the star formation process. So the Big Bang started in this, soup of particles and light, and then gravity and interaction created those larger structure, and in which galaxy formed and stars first formed. And the first stars that formed in those really first clouds of gas and what we might imagine be the first small galaxies, they were different. They didn't have the same chemical composition because, of course, right after the Big Bang, the universe was mostly hydrogen and helium, those tiny little elements. And as time continues to go forward, the galaxy merged, and as they were merging, the star formation process was continuously affecting and changing their chemical composition. And I like this video here because we see those small galaxies, and all the little blue dots are newborn stars, and eventually it turns to red when those stars get older. And so you can see that continuously the gas in green helps fueling galaxies star formation. And then with time, you get more older stars that build the bulge of the galaxies. But still, the star formation process is continuously happening. And sometimes it's triggered by those mergers of galaxies, but sometimes it's also happening just quietly in the disk while the galaxy rotates on itself. And I really like this video for that because we probably saw a couple of billion years going right there. But it's very helpful because it gives you an idea of the time scale of these phenomena happening. But those first galaxies also didn't look the way we see galaxies nowadays. And it's actually impossible to see them with great details, but this is an artistic rendering of what it might have looked like. So the first small galaxies with those stars forming that were different with that chemical composition that was different, helium and hydrogen. But not only that, those first stars were likely more massive. More and more studies are showing that the first star could have reached masses that were 1,000 times as massive as the sun. And these masses are literally impossible today because the universe chemically changed. And we cannot form these stars like that anymore. And I forgot to mention during my introduction, but you're welcome to use the chat to ask questions. I saw there was one question and I just missed it. So where on that map the TMT will go? Oh, I can go back and answer that. Give me a second. So I was at the summit. There you go. So this is the, well, I actually didn't put, yeah, okay, it's over there. So you see, you have the access road. You do have the James Clerk Maxwell, the GCMT right here. You have the SMA little antennas, and there's a road here that goes down into that plateau. And so TMT is supposed to be in that area down here. So you're welcome to use that chat box anytime. And I'll try to catch the other questions on time next. Yes. And let me just go back to the right slide. Okay. Perfect. So, okay. So this process happened continuously, the star formation process. And if we look at the universe today, this is a really nice image, the deep space image from Hubble Space Telescope. We see all these different galaxies with different shape, different colors, different stellar content. And of course, we know that they are all categorized in different kind of pattern. We have the spirals, the Baird spirals, the elliptical, and also the irregular. And so all of these galaxies form stars in different ways. Some are more passive. It is really well known that spiral galaxies, for instance, are forming more stars than the elliptical ones. And of course, the irregular tend to be smaller, and they can also form stars, but since they're smaller, they don't form as much stars in mass. And of course, you have those weird galaxies that harbor like super intense shape that can be due to interactions and things like that. But let's just focus now on those star-forming regions. So inside those galaxies, you have those areas where the gas collapse because of the force of gravity. So all these little particles inside the gas really like attract each other and eventually form stars. And we're going to focus on that today. So this simulation will show you a cloud of gas in a galaxy. This cloud is gigantic. It's about like 100 light year across. So 100 light year is really, really big. The solar system wouldn't even be resolved on an image like that. And now I'm just letting it go. So this simulation includes the physical mechanism that leads to star formation. So you have the gravity, you have turbulence, you have viscosity of the gas, you have the temperature gradients inside the gas. And as it evolves, you're going to start to see some little white dot coming out of the simulation. Those are the stars emerging. And of course, they are formed in the denser part of the gas, which are shown in yellow here. And they form in groups. So a cloud like this can form tens, hundreds, thousands of stars at once. And by saying at once, I mean within a couple of million years, like 1 to 4 million years of evolution. And some are ejected. You can see some stars going here and there. And they are all formed through the same cloud of gas. So they're like sisters. They have the same chemical composition, which is basically the chemical composition of the gas in which they formed. Yes, I see a question here. I heard on a recent James Webb Telescope that it would enable astronomers to look back from 500 million to 200 million years after the Big Bang. How much new data, photo, or spectra could that enable for the star forming time said to be? Okay, so that's a really good question. So the James Webb Telescope is going to be looking in the infrared and far infrared. As we know, when we are looking far in the universe, and since the universe is expanding, the light coming from those super far away objects takes often millions of years before reaching us. So to be able to see back into those first millions of years after the beginning of the universe, you really need to be able to see objects that are super far. And their light was also stretched by the expansion of the universe. So light that was maybe initially emitted in the visible or the ultraviolet got stretched and became the infrared and the far infrared. So to see in great detail objects that are super far and being able to study them in spectroscopy and imaging, you really need the bands that are inside this space telescope, the James the new Webb telescope. And so this is really going to help study those objects that are really far away in the universe in great detail. I cannot give you much more than this. I'll be a little bit like you, waiting for the first papers to come out to familiarize myself with the new data. And I'm working in the visible, and you're going to see why I'm more specialized with the visible light with Stell. Okay, so now we have this star stellar cluster that just got formed. This is a real image, the Rosette Nebula. And I like it because you see those blue stars, young stars in the middle, and you can still see the cloud of gas surrounding it. And why we see this cloud of gas with these magnificent colors is because there's inside massive stars that are shining and heating the gas, enabling the gas to emit its own light. And that's what we see. And that's a pretty powerful tool to study star formation, because when stars are forming, you have a whole range of masses of stars. And depending on what is formed, it's going to change the interaction between the stars and the gas. And this is another simulation that shows a more massive region getting formed. And it's a little bit more similar to a nebula like the Tarantula Nebula that we see right here, which contains some of the most massive stars known in the universe. And those are about 130 something solar masses. So not quite as massive as those first stars that might have formed in the early universe with like 1,000 solar masses, but still like 130 solar masses. And so by having those supermassive stars somewhere in the stellar cluster, they really emit a lot of light, a lot of high energy photons that are capable to heat up the gas and create those beautiful nebulae that we can see at super far distances. So that's a tool for me to study star formation in other galaxies, because I can see them very easily. I can study them in great details. And the gas is more extended than a star, of course, so I can detect the gas more easily than I can detect a single star. And those stars have a range of masses. So when they form, they are following a distribution of mass that we call the stellar initial mass function. So the stellar initial mass function, we often call it IMF. It is basically that function that drives how many massive stars do you have in a cluster with respect to the small ones. So you always have a bunch of small ones, like smaller than the sun. You have some that are about the mass of the sun, and a few that are more massive. And those more massive ones are actually very important, because massive stars, unlike the lower mass stars, they have stellar wind, very important stellar wind. They push a lot of matter outside into their surrounding, and they also end their life in a very catastrophic event such as supernovae. And then they push again all the new elements that are formed inside the stars by those nuclear fusion processes into the surrounding interstellar medium. And so all of the new elements like carbon, nitrogen, and oxygen that are formed in those stars very efficiently are pushed into back into the galaxy and can pollute the gas or enrich it, depending on which terminology you prefer. And then this gas that is enriched by those new elements can form new stars that will be different. And so massive stars for me are really the key here, because if they're there, they warm up the gas around them, I can see them easily. And also by studying them in great detail, we study that chemical enrichment processes. And I like to show this, periodic table of element, because you might have already seen it before, but I'm gonna have you like focus on the green colors. So you have the Big Bang elements, hydrogen and helium right there, a little bit of lithium. And then all the elements that are, very useful to life and other things are, at the beginning here, and they are mostly product by the explosion of massive stars or the explosion of white dwarfs, which are also, stars a little bit smaller masses, but still, important in star formation processes as well, but different process. And you can see also the dying low mass star in yellow are super contributing with a lot of elements. And then you have more exotic elements further out that are created by very extreme events, such as the merging of neutron stars. But you see how important those massive stars are. And so studying the star formation and also studying what is the ratio of massive star versus the low mass star, and how this evolved through the universe time, and how will this change if the condition in galaxy changes, while we are continuously enriching the galaxy with new elements from those stars. How is this affecting the star themselves, the next generations of stars? So this is what I really, really like to study. And I'm going to show you other simulation here, because I was telling you about how it is important to see those stars heating up the gas around them. And the physical process that is important here is called photoionization. It's a very fancy word to say basically that the photons coming from the star that we can see, it's at the center here, the photons coming from that star are propagating into the interstellar medium, and they are colliding with the atoms that are there, mostly hydrogen, of course, but other elements from the stars that have enriched the medium before. And when the photons have a high energy, an energy that is above the threshold to start kicking out electrons from the atoms, then what happens is the process of ionization. So when I say ionization, it means that an atom has lost one electron or two or three by this mechanism where photons are just hitting atoms, and kicking out electrons. And if you have a larger star, even more massive, of course, the bubble in which this phenomenon happens is going to be larger because you have more photons to kick out those electrons. And those bubbles are basically in the state of plasma. So when you ionize atom, you get a plasma bubble. So if you probably have heard that word much more often. So plasma is literally atoms that are ionized. And you can create that in a, some people have plasma lamps. You basically have the electricity that triggers that same phenomenon to happen in a plasma lamp. It ionizes the gas inside the plasma lamps. And you can see, and it also happens in lasers. So if you have a laser pointer for a presentation, for instance, it's the same thing that happens inside. So you have electricity that triggers that ionization. And then what happens inside those gigantic bubble of plasma, so you have the atoms that have lost a couple of electrons, they're there, and they can then shine by another mechanism. So you have all these free electrons that are going super fast. And they also then collide with the ions, with those atoms. And those little collisions are just enough so that, and I'm gonna stop like sharing because I need you to look at me like I think it's easier to understand that mechanism. So you have those atoms that have lost electrons, and then they collide with those tiny electrons that are just everywhere. And when it happens, there's still some electrons on those atoms, and it just pushed them away a little bit, but they still are bound with their atom, and they get pushed a little bit on another state, but it's not a stable state. And then they want to come back to their normal, like steady state. And when they come back, they always come back in the same way, jumping from one layer to another, emitting one photon, one particle of light at the exact same energy, the exact same color wavelength. And so when you look at those nebulae, you continuously see light coming from those electrons moving around because there's those free electron colliding. And just like in a laser pointer, you can have a red laser, a green laser, a blue laser. Well, in the gas of those bubble plasma, you have different colors that are basically like laser, and they are all associated with different elements that are ionized differently. So if I see a color, if I see red, and I can see it precisely with spectroscopy, I can tell you what atom it is and what triggered this emission. So it is very useful to study it. I see a question here. What happens to the electrons that are emitted? Exactly. I just answered, so you got it. And so I'm going to start again sharing the screen, but this is actually very important, and it leads to a lot of the science that I do, and that's why I wanted you to understand that mechanism. And so those bubble of ionized gas are basically the emission nebulae that we see around new stars. And so now you know that inside laser or inside those neon lamp, you have the same phenomenon happening, and depending on what is the gas inside those tubes, it emits different color. And it's the same in a nebulae. So if I see different colors inside a nebulae, I can associate it with the state of the gas or which atoms are there. And for stars, it's different. The stars emit all the different colors. So just like the sun have all the colors inside the rainbow, the star inside this cluster also have the same kind of emission. And now if you want to understand really deeply what's going on with knowing that you can study the physical processes inside a star-forming region using both the stars and this gigantic ball of plasma. So you need a couple of ingredients to understand what happens. You need to understand very well, what are the stars inside? Are they big? Are they small? How many they are? What's their mass? You can then have an idea of how many photons are emitted by those stars, creating that plasma bubble. And then if you know how much gas, or what is the density of the gas surrounding them, then it really helps you to see how big is going to be that bubble and how well it's going to propagate, how well those photons are going to go through the gas. And of course, then you need to know the abundances of the elements. How much hydrogen do you have with respect to carbon, nitrogen, oxygen, and others? And And of course, the electrons that I was talking about, the ones colliding everywhere, are super important. And you can measure their properties as well when you study the light coming from those regions. So this process, like creating that plasma bubble, it happens actually very quickly when a star is born. So you have the cloud collapsing, forming a star, the nuclear fusion start in the core of the star. And then within a few hundreds of thousands of years, this plasma bubble is going to be generated. And it's going to survive for a couple of millions of years. And a couple of millions of years for a galaxy is not a long time. So you can imagine this galaxy here as it's another simulation. A galaxy rotates like this on itself every 250 million years, more or less, like the Milky Way, for instance. And all those little red dots that you see are those plasma bubbles that are continuously getting lit up by massive stars. And then as soon as the massive stars explode in supernova, and it doesn't take that long, it's 1 to 40 million years before a massive star explodes in a supernova. Well, then the plasma bubble die off and you can't see it anymore. But it happens constantly, mostly in the spiral arm of galaxies, of spiral galaxy. So now you have an idea of how it happens, how much time it takes. And let's talk about those size, the different type of region that we see around us. Everybody knows well the Orion Nebulae. It's super close to us. It looks gigantic in the sky. You can see it with a pair of binocular. But in fact, the Orion Nebulae is actually an ultra compact star forming region. We call that H2 region because the hydrogen is ionized. It's a fancy word, but it's a very compact H2 region. It is only 4 parsec across. I hope you know parsecs. A parsec is 3.26 light year. So you can do the math if you want to know in light years. So 4 parsec is actually a pretty small bubble of ionized gas. Just in comparison, if I jump to another galaxy, this is a small galaxy that is about 50,000 parsec away. And this region here, I like it because it's like a perfect circle. This region is 100 parsecs, so it's 25 times bigger in diameter than the Orion Nebulae. And we can continue and go further. Like there are like always regions of different size in each galaxies. But if we go even further, and remember that little bubble of 100 parsecs, I'm going to use it later. But let's just check at a galaxy that is now 3.5 million parsec away. This huge complex of ionized bubbles is about 1,000 parsec across. And now on this galaxy here, oh, and yeah, and this one right here would be about the size of 100 parsec, by the way. And now on this one here, this bubble here is actually about 1,000 parsec. So in comparison, you know, it's gigantic when you think about it. And Orion is just a very, very tiny, tiny little thing. And just to help you even foresee even more that comparison, I made a code for analyzing those regions. And this code is selecting areas and basically finding all the different structures and different plasma bubbles in galaxy. And finding their neighbors basically, you know, to be able to study them separately. And if I look into these areas, and now I'm going to zoom in into this little corner here, which represent this tiny little area in the galaxy. And now we're looking at this one here, which is about 100 parsec. Well, on this image, if you try to see a region like that, or you would try to see Orion, it would be much, much different actually, up to a point where you could still see the 100 parsec region, like it would be just a few pixels on your image. But Orion, forget about it, you cannot detect Orion. So when you look at galaxies farther away, it really is important to know that you have a limit to what you can detect. And Orion is a compact region, and you can forget about detecting those regions at that distance. And there's also a lot of things that you need to incorporate in your science when you're studying them. Let me see how much time I have. Only a few minutes left. I'm going to go at fast speed because I want to talk about signals. And this is leading to signals. So those star forming regions, they are swimming into an environment in galaxy where you have other stars, you have gas, and depending on where you are, you have different air, like different things around you, different surrounding. And you also have what we call the diffuse gas, which is a little bit everywhere in galaxies. And this gas is ionized by other processes that are not necessarily star formation. And this contaminates your data when you're trying to study only the ionized areas inside the star forming region. So let me fast track, because I really want to leave enough time for questions. Can someone just give me an idea of how much time I have left before I can leave time for questions so I can balance my presentation?
Lori, you take whatever time you want, okay? We're
Really?
enjoying this immensely, so we're all yours.
Okay. Well, I'm at the third, so I'll try to go a little bit faster. But I don't want to scare you with like the amount of content that I have. I always have too many slides, by the way. But yeah, so here is another thing that would probably help you really understand the complexity of studying those regions. And so, when you're looking into the interstellar medium, the gas and galaxies, you have different area that can be hot, can be warm, cold. It can form molecules in the very dense area of the clouds. And then you have some stars that are forming usually very close to those dense clouds, because you need to have like enough material, and it needs to be dense for the gravity to kick in and form stars. So those stars are forming there. They start shining. They start to do that photoionization, and they eat up the cold gas and transform that cold gas and warmer gas into those plasma bubble. And okay, they have different temperature, they can have different density, different composition. And then on top of that, when you look at them, when you look at a plasma bubble or an H2 region, like the name, the scientific name for it, you can have a star that can be super high temperature or like medium temperature. And because it's like let's say a star that would be a B-type star, which is about 10 times the mass of the sun, or a little less. So this star produces enough photons to ionize things around itself. But if you have a star that is a little bit more massive, then it ionizes it differently, a little bit more intensely. And of course it goes on, the more massive the stars are. And then you can have multiple of them located in different areas of the cloud. And depending on what is your point of view, where are you looking into that region and from where, and what is crossing your line of sight from your telescope to the region, you're passing through different areas of the interstellar medium, which contaminate your data or which absorb sometimes part of the light. So that makes it a little bit more tricky to study. But fortunately, we have SIDEL. So SIDEL is perfect to do this kind of study because it is both doing spectroscopy and imaging of the targets. So this is SIDEL on the telescope. You might notice the resemblance with Espion at the Montmégantic Observatory and all the parts that are inside of it. And I'm going to go quickly and explain to you why it is special and why it is capable to do both imaging and spectroscopy. And I love showing images. So this is me pushing SIDEL on the summit in the dome. We have this team that are helping us doing the instrument exchange and putting SIDEL on the telescope. We have the development team here, and we have Julie Mandard, the engineer that was leading the project in lab to build it. So she was the lead engineer for building SIDEL. And so inside SIDEL, what is special is that you have what we call an interferometer, a Michelson interferometer. It might sound scary, but it's actually very simple the way it works. So in an interferometer, you have the central part here, which is called a beam splitter, which basically splits the light into equal components. So if you have a light source, a laser or anything that emits light, it goes into the interferometer. It's going to hit the beam splitter. Part of it's going to be transmitted, part of it's going to be reflected. And then on each part, on each arm of the interferometer, you have a mirror. One is not moving up there, and the other one is the movable mirror or the moving mirror. And then you can move that And once the light bounced back on the mirror to get back to the beam splitter, the same thing happened. And depending on the difference between the length of the two arms, it might do interference. So this is gonna play a little video that will show you what happens when we move the moving mirror. So you have the light here, the light wave, and as we move the mirror, it changes the phase of the light beam. And then instead of measuring a lot of light on the detector, you start to lose the light and you measure no light. If you start moving the mirror again, it'll again come back up and you're gonna see the light coming back again. So it's basically measuring the interferences of the light created by the two merging beams that have different phase. So I like this little video here shows what happens in real time if you would be close to the detector. So it's basically measuring those fringes of light. So intense, dark, intense, dark, intense, dark. And these little graphs that shows the intensity modulating like this are called interferograms. And so this is what CITEL measure. We measure interferences from the light coming from the interferometer. And there's an acronym again. So the zero path difference is that position, very important position, where this mirror is at the exact same distance as the fixed mirror. So the zero path difference is an important position that I'm gonna maybe mention once or twice again. And so if you have different colors of light coming into your interferometer, you're gonna measure the interferogram that will look different because the light is different. And you can imagine having a source inside your interferogram, the interferometer that is composed of multiple colors, multiple wavelength of light. And what you're going to measure inside CITEL would be the combination of the two interferograms. It might look like this. It looks a little weird, I know. I got so used to it that nowadays when I see an interferogram, I basically know what kind of light has produced it. It's an ability that you develop with a couple of years working with the instrument. So the instrument is really capable of turning light into interferograms. And then there's a mathematical tool that I use with my computer to analyze those interferograms and bring them back into their spectra. So this is a spectra of two emission lines, like two lasers coming from different colors, like a red and a green. And so if I see this inside CITEL while I'm scanning the movable mirror, I will be able to find back what is the color of the light. So that's the principle. And you can imagine that you'd have all the colors from the rainbow coming into CITEL, and the resulting observation would look like this. You might see that pattern familiar because it's exactly the same phenomenon that happened when you're looking at the surface of bubbles of soap. So there's actually interferences created in the layer of water and soap on a bubble, and you see the same colors. And so, yeah, before going too deep into this, I'll show you at least what it looks like one observation. So if we're looking at that nebulae that we observed for the first time with CITEL, the signal coming from the instrument on one tiny pixel of that image, there's actually multiple images that are taken. There's an image for every position of the mirror. And so if we take just one pixel of that image and we look at the intensity changing as a function of the position of the mirror moving, we can see those interferograms that look amazing. And you can see also the position where the two mirrors were at the same, it's the maximal flux is right here. We can see also the effect of the air mass changing. So as you turn the telescope and you have more light absorbed by the atmosphere, you can see that as well. And this is just another target with another interferogram. So the data, the raw data look like this actually. But don't be worried, after the analysis of the data, they look just normal. And of course, in a Michelson like this, there's a problem. There's a very, very big problem for astronomy because you see the light is going into this detector, but just as much as there's light going here in that pattern, there's also half of the light going back into the source because the beam splitter is also transmitting here or reflecting here. And in astronomy, you cannot afford to lose half of your light. So Sitel is slightly different than a typical Michelson. It's tilted a little bit more. And so you have the beam splitter, you have this the fixed mirror, the movable mirror, and you have two detectors that detect all of the light inside of the instrument. And so that's really the key here. And yes, I'm just gonna go like, so since it's tilted, instead of seeing that bullseye, like I showed you earlier with the Michelson, we're a little bit looking aside from the bullseye. So this is what we see. And if you shine a laser, like a green laser here inside Sitel, you'd see something like this. So these are the two detectors. So detector 1 is here, detector 2 is here, detector 1 here, detector 2. If you are close to the zero path difference, you'll see the light shining from one detector to the other. And if you're really far away from it, you're gonna see a lot of fringes like this. And believe me, when there's a light colored fringe there, it means there's a dark one on the other side. So if the light goes on one channel, it's not on the other, and so on. And I see, yeah, how quickly is the moving mirror? So the moving mirror is actually the most tricky part inside the instrument. Because we are constantly verifying its position 10,000 times per second. It has to be super precisely positioned, because if you're just ever so slightly not perfectly aligned, you lose completely this phenomenon of creating interference with the light. And so we have a system that we call a metrology system that continuously measures its position in 3D. And we have piezo in the back of the mirror that correct in real time, 10,000 times per second, the position of the mirror so that it's perfectly aligned. And so how quickly it is moving, it is at a very, very precise position. So the movement of the mirror is very small. It's like micrometer or nanometer. And then the precision is even smaller than that. And they're corrected constantly. Okay, moving a little bit forward again. So just to show you how like powerful this is, I'm going to show you an interferogram building up as we take observation. So we're just going to follow one pixel of an image. And as I'm going to play this movie, you're going to see one data point getting acquired here. And this is the interferogram. And on the other side, you're going to see the resulting spectrum. And you'll see the more data you have here, the more your spectrums start to look nice. And the more you see the light coming from different components of the gas. And this is, I can tell you here, this is hydrogen, this is nitrogen, this is sulfur lines. And I can also tell you that this is coming from a supernovae remnant, because I recognize the signature, a typical signature of a supernovae remnant here. And the more we have images, the better the spectra look. So it is a very powerful instrument because you can have like really high resolution on the elements that are emitting the light in your nebulae. And you can also create pretty images. I mean, I take those cube of data. So each data set with Sitel is in the shape of a cube because you have hundreds of images. And so those hundreds of images are together forming this data cube. And you can look across the data cube to see your spectra and your interferograms. And then you can study the star forming region and look at the emission coming from different elements inside the spectra. And Sitel is also using filters, like the filters you might use in a camera, but inside each filters, I will have a spectra. So you're having like a window of spectroscopy inside each filters of different colors. I see a question. So I hear of a technique called speckled interferometry that is used in telescope. Or how does your interferometer use this technique? Oh yeah, speckled interferometry. Yes. So speckled interferometry is different. They often use that technique with images. So they take images with a system in front to block the light from the star, and then they will have the light around, and they're trying to detect a lot exoplanet with that. It's not necessarily related to the same technique as I'm doing here, but as soon as you hear that word interferometry or interferometer, it does mean that they are using the light to create interference pattern to get information out of it. So this is how those two techniques are related, but they're really, really different. And so within a cube, so I'm showing you an image here, but you can imagine that you can go across that image and take the spectra. So I can go across one pixel and extract the spectra and see different emission coming from different parts of the galaxy with different features that are associated with different things, either stars, emission from the gas. And of course, there are regions that are different. So you have regions that are star-forming regions, but that are considered metal poor, so they don't have a lot of heavy elements, or metal rich, closer to the center, where there's a lot of stars, and then you can see more nitrogen here and things like that. You can study the dynamics, so you can also measure if those emission lines coming from the gas move from blue to red and measure their velocity and create those beautiful images of velocity curves of galaxy. And you can even subtract model and study the velocity or the dispersion of the velocity inside your star forming region, which is also super useful to see how the gas is actually moved around by other phenomena that are more mechanic, like those stellar wind that really can push mechanically the gas out. And well, I said it's a data cube, so I can make a video out of it. So I'm going to show you the video now, going through the images of the data cube, and you're going to see flashes where we're going through those emission lines from the gas, the hydrogen, the nitrogen. And I can zoom in and show you areas, different areas of the galaxy. This is the center, this is at the outskirts. And you can see thousands of star-forming regions, and you can study them in great detail, spatially, but also with the information from the spectroscopy. Okay, so I mentioned earlier, we need to account for those things that are surrounding the H2 regions, those plasma bubbles, and we need to know a lot of information about them to be able to characterize them, to study them, all those elements. So by having CITEL doing imaging and spectroscopy, we can do a lot of all this, which other instruments before were not capable of giving you all this information at once. So this is really the power of CITEL. And with that in mind, this is why I build with my team of collaborators the project Signals. So I am the project investigator of Signals, and I have a team of co-PIs. You might recognize my advisor for my PhD, Camille Robert, and Laurent Drissen, who was the PI of Espion and CITEL. Here is another Québécois, Canadian from Gaspésie, René-Pierre Martin. He works in Hawaii as well with me. And this is Philippe Amram from France. And we together built that program using the strength of CITEL, in the sense that we knew CITEL was capable to do this science for the first time. And we wanted to use it in an extended survey to study star formation in the nearby universe like any other have done before. But this is a much larger collaboration. So by building this project, we seeked for professional and specialists around the world, other astronomers that study different aspects of star formation. And our team is now built up about 70 people from 17 different countries. We're a little heavy in Canada, of course. And we have a lot of people from France and Hawaii, because I work for the Canada-France-Hawaii telescope. But we have people literally from different teams that are interested in different aspects of this phenomenon. Some people really are interested in the young stars. Some people are really, really focusing on those photoionization mechanism. Some really want to study the dynamic, the motion in the gas and galaxy and things like that. And I could give you other examples, but this is why we need so many people involved into this. We did a first meeting just before the pandemic. This is a part of the team, the Signal team. We met in Canada. And why do we want to study all these star forming regions from different galaxies in the surrounding universe? So just to give you a quick overview of why this is so important. So there are many things that we still don't know about the star formation process. For instance, we often study it to, of course, study how galaxies evolve chemically, because stars are forming new elements. They distribute those elements and then form new stars, but those stars are now transformed by this phenomenon. But then how does it affect how many stars are formed? And this is what we call the star formation rate of the galaxy. How many solar masses of material is transformed in star constantly? And then we also want to study the efficiency of that. And what is the efficiency is, because we know how much gas there is in galaxy, and we know how many are formed with the star formation rate. If there's a lot of gas available and only a few stars forming, then this is not really efficient. Whereas in some galaxy, you have only a little bit of gas and most of it transformed very efficiently. So we want to study that and why in some areas it is very efficient and some in others it's not. Then, of course, the stellar initial mass function, the IMF that I was talking about earlier. So how many massive stars are formed versus the small ones? And mostly within those massive stars, how many super like hundreds of solar massive stars are formed versus the ones that are about just 10 solar masses and things like that. And this is very important because they are really the driver that forms those elements from the periodic table, carbon, nitrogen, oxygen, and things like that. And so really understanding their population and how they form is the key of signal. And I see a question here. So based on an optimal seeing and assuming the largest star forming regions in a galaxy, how far out can you get useful data? 10 megaparsec, that's the limit of signals. I'll tell you why in a few slides. And so these are also the phenomenon that are really important within signals. So we want to study abundances in galaxy, how it get enhanced and enriched by star formation. So that's what we call metallicity, like how many heavy elements are produced. We have elements that are produced by massive stars, and those by lower mass star, those planetary nebulae and things like that, those are important too, and they're different. We want to study the interstellar medium, its density, its temperature, its ionization mechanism, and how it fills the space. And we want also to study everything that is around. So either there's other ionized gas surrounding those regions, or there's populations of stars of different mass, ages, local density. So is there a lot of stars or not a lot of stars, and things like that. So these are things that we want to tie to our analysis of star formation in galaxies. And of course, it is important because galaxy lives in different environments, and inside galaxy, you have different environments. Sometimes you have lots of stars, sometimes you have lots of gas, sometimes the star formation is really active, and sometimes it's not. And just to give you an idea of what it could look like, here's a few images of star forming regions in different areas of the galaxy M33. Nearby the center, where there's a lot of stars, in outskirts where it's very low stellar density. You have larger regions, smaller regions, some that are, the green yellow ones are often produced by more massive stars, whereas the little red ones are often those stars that are like probably 10 solar masses. They're on the edge of being able to ionize the gas, and they're still massive, but not as massive definitely as those that could be inside those yellow bubbles. You have gigantic, extremely large regions that are forming thousands of, like tens and hundreds of thousands of stars, and the ones that form one star, one massive star at a time. And some are close to gas, some are far away from filaments of gas and things like that. So Signals is targeting 50,000 regions like these in the nearby universe and about 40 galaxies that are close by at a limit of 10 megaparsec. And we're doing that because at that distance, we can still see a lot of details and study them spatially. And the reason why you want to study them spatially is obvious, like because you can see what's going on, but just to quantify it, like when you're studying regions inside the Milky Way, like Orion, you have so much detail about everything. You can even see every little star in Orion and study each star separately and study a lot of things inside of it. If you go to M33, then you start losing a little bit the resolution, but you have still a really good idea of what's going on. You can study the extinction from some filaments of gas that are blocking the light from you. You have abundances from the gas. You have the mass from the stellar cluster inside each of the regions. And you also know what we call the spectral energy distribution. This is a fancy word to say, you know how many photons are there to ionize your plasma bubbles. And as soon as you go farther away, you lose that information, and then you can't see anything. So you need to do a lot of assumption and hypothesis on what's going on in those galaxies. And if you're trying to target the same galaxy that the Webb telescope is going to target in the faraway universe, those red galaxies that are like little, they look like little fly on your image, well, you can't see anything. So you need surveys like Signals to tell you what it might look like and give you the best idea of what it might look like in those galaxies. And lots of surveys are doing that. Often they are at about that spatial resolution over here. This is the range of Signals spatial resolution. So it goes from super detailed to somehow detailed. And the limit that you see here is basically images that would be at 10 megaparsec. So that's why we're not necessarily looking at galaxy farther away than that. And still looking at my time, like just to make sure I'm super busting my time. Let me see, just to conclude a couple of things. I'm gonna show you, yes, at least this one. This is an impressive data cube coming from one field inside the M33 galaxy. So it's not the whole galaxy, it's just a part of it. And Citel has a very large field of view, but M33 is very, very large. So we have to do a mosaic of it to fully cover the galaxy. And here you see the gas inside that spiral arm that is right here. And you see all the regions inside of it. And you can see here, we're gonna hit the hydrogen line right there. And so these are amazing data set that I get to study. And right now we have 3 years of observation in bank. This is what it looks like. You might recognize the mosaic of M33 is here on this side, and you have other galaxy on the right side. We're about halfway through the observing of Signals. We have another year to go, but this year is a very busy year where we have a lot of observing time. And within the data already acquired, we were able to detect 30,000 regions of those ionized bubble, the H2 regions. So 30,000 star-forming regions that contain massive stars. That's a lot. And we plan to double this number by the end of the survey. And this is just another example of another galaxy here. And I'm going to show you at least one slide of some of the results that are, I think, very interesting. Let's pick, I'm going to pick, that's the hard choice to do. Let's go with this one. Okay. So within all of these regions, we have 3 different strategies to study them and understand what's going on. And I kept saying, you know, we are trying to understand star formation in different environments inside galaxies. So we want to study groups of regions that are in environment that are similar in galaxies. So you can imagine within those 30,000 regions that we've sampled, thousands of them are in center of galaxies where there's a lot of other stars around. So we can group them together and see what they look like. Are they different than the other ensemble of regions that might be in the outskirts of the galaxy? Then we have we're sampling different metallicity and chemical content. So we can decide to split up again this group of regions that are in the center of galaxies. And we can look at the ones that are metal poor or metal rich and see if their characteristics are different. This is really what's going to help us study this whole phenomenon of star formation at a really large scale. And so to do that, we have 3 different strategies. One is studying the whole population as together. So we compare the chemical abundances from different elements. And we know that if a group of regions have a shape that looks like this, then it means something about their initial mass function. It means something about their metallicity. It means something about a lot of the parameters that are linked with the characteristic of the region. Then we can study each region separately, like by just grabbing all the flux inside one region and look at where they land on our models. And our models are what we call those photoionization models. So they are modelizing those bubble of plasma and telling us how the plasma bubble should look like if we represent well the characteristic of the region. So those models are really helping us to find out what is the mass of the cluster, what is the abundances inside of the region, and also what are the density of the gas and things like that. And finally, we can do models one region per region, and then we study not only the full emission coming from the region, but what it looks like spatially. So if you remember that 100 parsec region that I showed you earlier in that small galaxy, this is it here in different colors with a model that compare what we can reproduce using what we know about that region. And this is just one example. I think it's a really powerful tool. We have about 10 teams working on different aspects of signals, from modeling those plasma bubble to studying the young clusters, the stellar populations inside galaxy, the dynamic, the star formation rate, and some feedback from supernovae and structures like galaxy spiral arm and bar and bulge and things like that. And it's really going to be active within the next few years, since all of the results are going to be published, I hope, as soon as possible, also to be able to give data to the public. So all the results coming from those teams are going to be available through our website. So that anybody who has an idea of things that they can do with this data set can do it, because there are much more than just studying star formation that can be done with the data from STEL. So if you have an idea, just follow what's going on our Signals website. I'll send you guys a link on the chat in a few seconds. And I really hope you enjoyed the talk. I'm going to conclude by just saying that when I was super young, I was spending a lot of time outdoor with my dad. We were hunting, fishing, hiking, and this is actually the place where we go hunting every year. I was there a month ago. I took vacation to go moose hunting with my dad, like we do every year, and some of my uncle and aunt. And spending time outdoor is really what triggered my curiosity and made me a better observer. I think being in the nature really put you in a state where you're really attentive to details and you really want to understand things around you, the environment, how it impacts the animals, behaviors, and how everything is connected. And I really think it helps me being a good scientist nowadays, even doing things that I do with signals. So I really think it's important to mention that spending time outdoor in Canada is really what was an inspiration for me, and I bet for a lot of other kids around the country. So I'll stop there. And I hope you have more questions. I don't know if I missed anyone's in the question in the chat. Let me check quickly. Okay, do you concentrate on spiral so you can get? Yes, we do. We do not look on the Aegon spiral because of the dust reddening, exactly. So I hope you enjoyed it and you have more questions for me. I'll be happy to stick with you for another 10 or 15 minutes, I guess. Thank you.
Lori, no, thank you. That's, first of all, an incredibly ambitious and very impressive project.
Thank you.
Yeah, you should be very proud of this because the results you're yielding are really, really impressive. And you've done a fantastic job explaining it tonight. And certainly your passion for it comes through very clearly. And that's so exciting to see. It's so exciting. So
yeah. I guess here we all love astronomy.
Oh, yes, absolutely. You're right. Yeah, absolutely.
So yeah, you were not too much of a hard public for me.
So is there anybody out there with any other questions? And Chris, do we have any questions coming in from your sources there?
There are none on my side.
So, okay. Anybody else with us live here right now that has any questions? So there's one that's come through on chat.
Yeah, I can see that. So what is the typical integration time per sub-image as a mirror is being moved? So it depends on the filter. So typically Signals is using 3 filters for covering the emission from the gas that is really interesting for us. So in the blue, we have about 57 seconds, and all the way up to the red, which is the lowest integration time, which is 13.3 seconds. But they don't have the same spectral resolution. So we have 840 images in the red for covering that spectral range to have super high resolution on the velocities of the hydrogen line. So the spectral resolution is 5,000. So 13.3 seconds per step, but 840 images total. Whereas in the blue, we have much more time per step, but fewer steps, about 172 steps in that case. Yes, I see. I heard that the James Webb will be capable of both photographing and spectroscopy. Yes, that's right. Oh, that's a good question. So I would have to review it. I am not sure of exactly their instrumentation project inside the James Webb. But I would be happy to review it and give you an idea. I wouldn't be surprised if it was a similar technology, because it is more easy to really measure and correct the position of the mirror in the infrared and far infrared. The precision that you need on the position of the moving mirror is less constraint in that wavelength range that it is in the visible. So it is less tricky to build an instrument like this for the infrared and far infrared.
Or may I ask a question? In selecting the targets, how have you gone about the approach to, because this is a project that's taking years of data acquisition. How have you gone about your approach to where your early targets are compared to your later ones? Are you moving geographically through the sky? Are you moving out from near to far? And as you do that, are you learning as you go and finding that that the later data acquisition is are you applying anything you're learning to it to yield better results as you go?
Yeah, that's a super good question. So we had actually a sample of galaxy that was larger than the amount of time that was allocated, because we were aiming at building about 50,000 region within the sample. And if I would be able to observe all the available galaxy within that volume of 10 megaparsec, it would have taken probably twice as much time. And you know how much time is expensive, so you really have to be able to justify that. So we stuck with, we decided to stick with the 50,000 region sample. And as we observe, what is important for us is to really sample these different environment and galaxy like relatively uniformly. And so if I have a couple of large galaxy in my sample, those large galaxy can have thousands of star forming regions in them. Whereas if I look at a small galaxy that have lower metallicity, lower stellar content and everything, they also have just often like a few tens of star forming region. And I want to sample that environment more because 10 region is not enough statistically to fully understand what's going on. And so in our sample, we only have a few massive ones, and we do have a lot of those smaller galaxies to be able to sample those properties of the environment. So that really led and drove our selection. So the amount of star formation in a galaxy and the properties that were sampled really is the trigger. And as we go, as we move on, I measure the amount of region, I measure some of the characteristic. And so we can fine tune the last year which target we need to fill what is missing in the sample. But it's not necessarily especially like we don't have necessarily a strategy across the right ascension or things like that. It's really driven by the science content and what we get from the data in the galaxy.
Excellent, thank you. And you know what? There's one more question in chat, so let's take the time for one final question.
Yes. Yes, I see it. Does your team make projection as to which area you observe are more amenable to the beginning of life as we know it? Maybe that's not your mandate. Yeah, no, unfortunately. Actually, you know what I like to say is the area that I look at with those plasma bubble and massive stars are definitely not friendly for life. You'd have like a blast of UV photons constantly, constantly ripping off your atmosphere if there was any planet there. So definitely not. Those stars need to be away and gone before life can ever emerge from those areas.
And that's the perfect place to wrap things up. I cannot thank you enough for taking the time to spend with us today. You're clearly a very busy person, and we very much appreciate that you've taken time out of your busy day to spend with us. You have a very appreciative audience here. I know I speak for everyone in thanking you and telling you how much we enjoyed it. Well done.
It was a pleasure. Have a nice weekend, and please send me pictures of your next astronomy project. I want to see it. Sometimes the pictures from astronomy amateur astronomer are better. I'm always impressed with what you guys can do.
It's a deal. So thanks so much.
Bye.
And everyone, so with that, was absolutely wonderful. Now we're not done for the evening. We still have the Sky This Month with Matthew Mannering to come. We have some door prizes to give away, and we have a little bit of club business to wrap things up with. So by all means, I'm sure at this point everybody's ready for a 5-minute break. So take the 5 minutes. It's just coming up on 9. We'll certainly be back no later than 5 after 9. To give away some door prizes and hear the Sky This Month. So don't go away. We'll be back in a few minutes.
Hey, John, we're at 9:05.
Yeah, I'm here. I'm just getting set back down here. So. Hi, everyone. So, all right. So, yes, as Chris has just reminded us, it is 9:05. So let's get back to it. So we have a few door prizes to give away here. And I want to remind everyone, if you were the recipient of a past door prize, I have a few unclaimed door prizes here. So please don't hesitate to get in touch with me so that we can get those back out into your hands. You can reach me from now till the end of the month at chair@amateurastronomy.org. Unfortunately, we don't have our wonderful door prize distributor here tonight. We usually have Maya Whitman, but we don't have Maya here tonight. So I've got a random number generator queued up here, and we'll do our best. So tonight we have some wonderful door prizes, including this one, very appropriately, Great Observatories of the World. Okay, this is a massive book. Okay, just based on sheer size, it's worth any 3 other door prizes. So it's absolutely huge. And yes, I did check, and it has a wonderful chapter on the Canada, France, Hawaii telescope in there. So it's a lovely book, and I've been saving it for this month so that we could do this while Lori was here. We've also got a copy of Night Watch by Terry Dickinson, absolutely one of the best amateur astronomy books that you can start with. And we have a copy of Explore the Night Sky right here, which is a magazine format publication. That's a wonderful overview into all things astronomical, right? Galaxies and nebula and star clusters and all that kind of stuff. So we have those 3 wonderful prizes. And this is going to be, we've got a random number generator, and I'm going to have to just count people down here, okay, to make this work. So we're going to select the first one. So the first name today is Bob Christmas. Bob, are you there?
Yes,
Hello,
I'm here.
Bob. Yours is the first one pulled in for a door prize. Congratulations.
Woohoo.
So congratulations. Well done. So, okay. And the second one pulled is Solange. Solange, are you there?
Yes, I'm here.
Hello, congratulations. You're a door prize winner.
Yay.
So, yay,
Awesome. Thank you so
indeed.
much.
So, and third one is, so how many people do we have here? We have 39. So, and third goes to, okay, so we are at, is Mike Hamilton. Mike, are you there?
Yes, I'm here.
So, hi, Mike. You want
Hi.
to prize?
Thanks. Awesome.
So, yeah, you're welcome. Fantastic. Okay, well, congratulations to door prize winners. I've got one more door prize here that I'm saving for the end of the night. Don't let me forget. So congratulations to the 3 of you. To the 3 of you, get in touch with me directly. You probably have my personal email. You can also reach me at chair@amateurastronomy.org to arrange for a time to connect, and you can come and pick these up. For those of you that have won a door prize in the past and haven't collected, I haven't given them away. They're still here. And by all means, please get in touch with me so that we can make sure that you get those. So, all right, fantastic. Next up, of course, we have Matthew Mannering. Matthew, how are you doing?
I'm okay. How are you?
So fantastic. Matt, by all means, please feel free to put your camera on, and we throw ourselves into your hands for tonight's edition of The Sky This Month.
Okay.
And just a reminder, sorry, just a reminder to everyone else to please put themselves on mute and to turn off your video.
Ugh. Hang on. Okay, can everybody see my presentation and hear me?
Yes, it looks great so far.
Excellent.
Yeah.
All right, so welcome to The Sky This Month for October 2021. I'm starting this presentation with a picture I took of the sun, unfiltered, on Monday. I was out birding and the sky was cloudy, as it has been for, seems like forever. I happened to look up and realized I could probably capture some of the sunspots on the face of the sun if I took a shot. This shot is unfiltered, meaning I just pointed and shot in full manual and realizing that the cloud was dense enough that I could do it safely. However, this is one of those do as I say, not as I do, or don't try this at home moments. If you don't know exactly what you're doing, then I'll let you know in a sec. Just the safer way to do this is the way I recommend for everybody. But here I've zoomed in on my picture at the top, and the pictures at the bottom are the same, just one is zoomed in a bit more. And this is the Solar Dynamic Observatory. This image is from within, I think, about 2 minutes of when I took mine. So I took my image and then went online and downloaded this to my phone. So you can see it nicely mirrors the sunspot group here and the large one, which had just appeared the day before on the limb of the sun. So there's a lot of solar activity going on right now. I've done a fair amount of solar observing with my actual hydrogen alpha telescope, and it's been really interesting. Battery is running low. Oh dear, hang on a sec. Just hang on. Technical difficulties for it. Here we go.
Matt,
We're good. We're good.
You got to hang in there with us at least until the end of your presentation.
I know, but there was only 10 minutes left on my battery. Apparently, I didn't have it plugged in since we had a power outage just before the meeting started. Anyways, so there is a safe way to do this during the daytime. The first thing to realize is you should really have a filter on the front of your camera. They're called white light filters. Some are for visual and photographic, and some are photographic only. I would recommend getting the visual/photographic one, because the ones that are just photographic let some harmful rays through. So if you happen to look and do something wrong, you're going to damage your eyes. So get the better filters. You can see here they're using their live view screen. You do not ever look through your viewfinder here, okay? Because when you do that especially on a digital SLR, you're looking right through the lens directly at the sun. And if you're really lucky, the worst thing that will happen is you'll burn out the sensor in your camera, and the worst thing is you'll blind yourself. So just don't do it. Use the live view screen, filter it, and then you can take as many pictures as you like. Here's an example of a glass filter made by 1000 Oaks. These are really high quality filters. They're in the range of $100, but they last a long time. They don't get pinholes in them very often. They tend to be really good. The other type, of course, is Mylar, and that's the type of thing you see in those solar eclipse glasses. But people like Botter make sheets of Mylar that you can then turn into custom sized filters for your camera equipment or small telescope. The other, I think we're going to talk about a couple of the missions that are either on their way or about to leave. This first one is Bepi Colombo, and it's finally arrived at Mercury, sort of. So Bepi Colombo's been en route for a couple of years. As it dives deeper and deeper into the solar system towards the sun, it's moving faster and has to find a way to slow itself down. So the way it does it is by doing flybys of the Earth first, then Venus, and then Mercury until it finally comes into a stable orbit. This particular probe is named after Giuseppe Colombo. I looked this up because I thought it was an interesting name for a probe. And he was a scientist, mathematician, engineer, and he was the guy who first proposed how to do interplanetary gravity assist maneuvers, otherwise known as slingshot maneuvers, which allows you to change your direction and your velocity of your probe to make it go where you want to go. And the cat is drinking my water out of my glass right beside me. This is very weird. So what are the objectives of this? Well, we're going to study the origin and evolution of a planet close to its parent star. Of course, it's very handy. We have planets close to our star, and they're not that far away. We're going to look at the structure of Mercury, geology. They're going to look into the atmosphere, including how it's created and how it escapes from the planet. There's two possible ways it can be created. One is from the solar wind, from the sun, and the other is by the decomposition of materials at the surface of the crust, which then release atoms and create a very tenuous atmosphere. Nothing like anything we would even think of as an atmosphere, but it's there. And then they want to know how fast it's escaping, for instance. And the other thing is this probe actually breaks into two different probes. One, the magnetic field and magnetosphere probe, stays very close. The other one, which is studying the geology and the atmosphere and stuff, has a wider elliptical orbit. So what is the difference between a magnetic field and the magnetosphere? Well, the magnetosphere is the region of space around the planet that's affected by the magnetic field. So whenever you see a picture with all those magnetic field lines around a planet, or similar to iron filings, when you see a magnet, they put the iron filings, they blow it up to planet size, right? Those magnetic fields work in a volume of space, and that is the magnetosphere. So this particular probe got off in October 2018. It made its first planetary flyby back in 20, and then it did 2 Venus flybys in 20 and 21. And just on October 1st, it did its first flyby of Mercury. So after that, it has another, let's see, 1, 2, 3, 4, 5 flybys to go all the way through January of 25. And then at the end of that year, around Christmas, it's finally going to settle into orbit around Mercury. At that point, it will really start doing its data collection and everything else. And end of mission is 1.5 years after that, possibly 2.5 years. It depends on how the probe survives in that environment that close to the sun. Now, what's really interesting is once you start thinking about these orbital mechanics and how does the heck does you get this probe to go in there, do all the flybys, and how do you get it to settle into orbit? Turns out if you go to that page from the European Space Agency, because it's them and the Japanese that are actually co-working on this probe, there's an icon here, interactive, where is Bepi Colombo? And if you go into that, you get something like this. And what it does is green line is where the probe is moved through space to where it is now from the Earth. What you can do is you can take this slider and move it all the way back to the beginning and then hit play. And if you have about 20 minutes, you can watch it as it goes through the changes in its orbit and spirals down towards Mercury. If you don't want to take that long, hit this button here, the setup button, and up here will be a slider. Push the slider all the way to the right. It says speed, and then hit the play button. And it will do it in a much more compressed time frame, but still easy to watch. And as the probe spirals in towards Mercury, you can use your mouse and zoom in to see the elliptical orbits and how they start to merge with Mercury as it goes along. Another mission that hasn't launched yet, but will very shortly, is called Lucy. And this one is the first mission from Earth to go to visit the Trojan asteroids around Jupiter. So Trojan asteroids are asteroids that share the same orbit as a planet. In this case, there's Jupiter, And there's Trojans that are ahead of Jupiter in its orbit and trailing. And there's a huge number of them here and here. This is the inner solar system. That little red dot's Mars, by the way. So the name for this probe, Lucy, comes from that skeleton that they found back in Africa in '74. I think a lot of us remember when that was found and it was announced to the world. And that was a very, very old skeleton that gave us some insight into human evolution. And Lucy is going to look into the evolution of our solar system, and that's how it got its name. Throughout the period of the whole mission, it's going to look at 8 different asteroids. One is in the main belt, which is that belt of asteroids between Mars and Jupiter, and the other 7 are Trojans ahead of and trailing Jupiter itself. And the reason they want to look at them is because those asteroids are believed to be remnants of the material that created the solar system in the first place, or from which the solar system was created. If you want to watch the launch, it's going to be on October 16th. Coverage starts at 5 a.m. and I believe the launch is at about 20 to 6 in the morning. So the reason you can have Trojans that stay in a stable orbit along with the planet is because they're at spots in the orbit called Lagrange points. Now, for any 2 bodies in the solar system where one orbits the other, you can have these Lagrange points, 1, 2, 3, 4, and 5. It only works if the body at the center is massively bigger than the next body. So the ratio of the mass has to be a minimum of 25 times. So, you know, the Earth compared to the sun, it's no problem, right? So here's the Earth, here's the sun, here's these Lagrange points. We tend to put satellites at L1, L2. And the nice thing is that L1 through L3, you can put a satellite there. And even though it's not exactly stable, it will slowly drift away from the Lagrange point. It takes a minimum amount of propellant to keep the satellite in position. And so you can have your missions last much, much longer than if they were just, you know, floating around at a non-Lagrange point. 4 and 5 are different. They're called stable points. And anything within this region of space, here or here, will tend to stay there for long, long, long periods of time. Now, if you've got multiple objects within one of these groups of Trojans here, they will move around with respect to each other. But they will tend to stay in their group. So you can have Lagrange points for the sun, Earth. You can have them from the Earth to the moon, or from the sun to Jupiter, for instance. Every planet versus the sun basically has its own Lagrange points. And here is a little animation of how it actually looks. The inner solar system there, the red dot's Mars. The asteroid belt, the main asteroid belt, would be in here somewhere. And these are all the Trojans trailing and leading that are ahead of and behind Jupiter in its orbit. So Lucy is going to visit both clusters, and it's going to look at 3 different types of bodies within those clusters. 2 of them are dark red asteroids, similar to those found in the Kuiper belt. In fact, probably very similar to the one that New Horizons took photos of a couple of years after it passed Pluto. The 3rd type they expect is going to be more like the main asteroid belt between Mars and Jupiter. So really, they're just trying to image these things and find out what they can chemically, whatever they can about them while they're running through the Lagrange point. Here is the actual mission summary. If you think about it, it's from when it leaves Earth to when it gets out to the Lagrange point here, L4, and it's going to look at a few different Trojans in here, or asteroids, and then it's going to come zooming around and look at least one over here. The interesting thing is this isn't random. These dots are specific asteroids within that belt, and that one over there is specific. So it's really interesting that they can be that precise in what they're going to do, and it should be a really interesting mission. Unfortunately, it'll be a while before it gets there. And a little bit about the sky this month. There's a lot of information. Bernie posted a ton of information in the event horizon this month about objects to look at all through this fall. Joanne's got a few that she mentions as well in her really good article that she wrote this month. And there's a couple of things in mind. But what I wanted to really talk about was how nice the sky is at this time of year if the clouds ever actually go away. So if you go out at about 10 o'clock at night, anywhere 9, 10 o'clock at night, into a nice field with good horizons, and you look out to the west, you're going to see the Milky Way coming out of the ground there, and you can follow it all the way, almost completely, like directly overhead, all the way to the east, the eastern horizon. So take your time, grab your binoculars. It's just awesome. You can sit back and just scan from basically the core of the Milky Way here, all the way out to the outer reaches of the Milky Way over here. So the core is what you see in the summer, right? That's that beautiful Milky Way shot you get with Sagittarius and Ophiuchus and that kind of thing there. So that's why it's really dense. There's all this material, clouds of dust, gas, stars, clusters, all sorts of things, right? But as you move across the sky, you're actually turning away from the core and looking out towards the rim of the galaxy. And so the amount of material is much less, so the Milky Way is much thinner, or there's less material there to see, but it is still there. And even in the winter, the Milky Way is still there. It is just not as obvious as in, say, July, when it's really amazing. Now, tomorrow night, just after the sun sets, you're going to be able to see the moon about 3 degrees away from Venus. The moon's going to be lit about 16%. You should be able to see some earth shine there. And one really nice aspect of this is that the libration of the moon, almost said libation, that'd be wrong. The libration of the moon is such that Mare Crisium, the Sea of Crisis there, is nicely separated from the limb and the terminator. And that's a sort of area that I don't think a lot of people look at enough. When I look at it through my binoculars, the crater rim, because really, even though they call it a sea, it's in a massive crater, right? It's very 3D. You can actually see the mountains around the rim differentiate themselves in 3D from the base, and that's just binoculars. If I zoom in here, you can actually see Mare Crisium much better there. There's a few of these seas that are around the corner, so to speak. What is it called? Mare Smith and Mare Marginis, the sea on the margin. They're there. You can catch a glimpse of them. Have a look at this, though, because when you actually get in close, there's a ton of detail here. So things you can see with the telescope are these ridges here, which are basically lava flow ridges, molten rock that's flown and then just caused this sort of a ridge as it ends. You can see where it's gone out the crater wall and has escaped over there. You can also see in Mare Crisium quite a few craters that have been filled by these flows here, there. There's quite a few of them. If you look around, they're almost completely been annihilated or submerged by the lava. And there's a few obvious ones like this one here, which I happen to remember is called Picard. That is very obvious. And then, of course, look at all of the detail and all of the structure around the edge. I think with a telescope, you can have a pretty good time, and the lighting will be very nice with this phase. The other thing I wanted to mention is that last third of the month, roughly from the 21st to the 31st, Mercury is in a really good position to view in the morning, and it's even not too bad a time. Somewhere between around 7 o'clock in the morning, Mercury will be about as high as it gets, where you can see it before the sun peaks over the horizon. So the sun right now in this image is right there. The reason this works so well is because the plane of the ecliptic is very steep in the morning here in the fall. So when the ecliptic is very shallow like this, the sun will be up, Mercury will be up, and very hard to see. But right now the sun is behind the horizon and Mercury is there right at the edge of the light dome, and you should be able to see it quite nicely. It'll only be about 8 or 9 degrees up above the horizon, so you do need a clear view to the east, but it will be there. And from what I've read, it's the best view you're going to get this year of Mercury. So, 7 o'clock's not too early. Take the chance if you can and see if you can spot it in the east. Maybe take a picture. And that's it. Thank you.
On the contrary, thank you, Matthew. Wonderful. So as always, so that was excellent. So that image of Chrysium from the Lunar Reconnaissance Orbiter, my goodness, that's something, isn't it? So,
It is. It's an amazing sea to look at, really.
yeah, it really is. And Crater Picard is named for the astronomer Jean Picard, not the starship captain. By the same
I did
name.
know that. I did know that, but it just
Yes.
stuck in my head.
I know you did. That's we all did. We all knew that, right? We
Yeah,
all knew.
that's it.
Yeah. So,
Yeah.
So yeah. So that's fantastic. Any questions for Matthew? All right. And you know what? I encourage everybody to check out the Event Horizon, the newsletter. Matthew's article that goes under the same name of The Sky This Month, and the newsletter is always packed with wonderful information and illustrations, and it is well worth checking out. Okay, so
John?
that's great. Yeah.
Just before you finish up, I just wanted to say, on behalf of everybody, really, thank you very much for all the work you've done as chair, because I know you're going to talk about everybody else pretty soon, but you won't talk about yourself. So I wanted to say thank you for all the work you've done, and it's been a pleasure, as always.
Well, that is very, very kind of you. So, and I won't, but you know what? But if anybody wants to call me up personally, I'll talk about myself till the cows come home. No problem. So thank you, Matthew. So there is one final little bit of business for tonight, and that is introducing the incoming council. October marks the end of October and the beginning of November marks the turnover of the club year. And just as we said, memberships are due. And we got a good comment from somebody. Those people that have just recently joined, you don't need to send in your membership again. If you've just come to us, this summer and into this fall, then your membership is good through the upcoming year. Okay, so you don't need to do that again. But for those of you like me who it's time to renew, and at the end of this month, we also switched council over to the next council for the 21-22 season. Chris, do you have that slide? Chris is going to screen share a slide, and there it is. There's the incoming council for the upcoming year. So the chair will be Bernie Vanasse. The second chair will be Chris Stretch. And those people are both moving into these positions new. Bernie's been chair before and will be taking over the chair again after I've been here for 3 years, and I'm sure you're ready for a change there. This is his first term as second chair, and I cannot think of a better person to put in that spot. That's just fantastic. Denise White is staying on as secretary. Ann Tkach is staying on as treasurer. Brenda Frederick is staying on as recorder. Chris Stretch is the mastermind behind the scenes doing all this stuff, and he handles all our digital platforms, and he'll continue to do that. Bob Christmas stays on as newsletter editor. Joanne Salsi stays on as education director. Paula Owen is going to join council as the new membership director, and I couldn't be happier to welcome her to council and to know that that position is going to be in such good hands. I'm absolutely delighted. Matthew Mannering, who you just saw deliver the Sky This Month, you're going to get a whole more extra year of the Sky This Month from Matthew, and that's great. And Mario Carr has handled the publicity for us for many, many, many years and is going to continue to do so. I want to give my congratulations to the incoming council. Other members who will join as councilors at large will be announced next month. And there are still others beyond this who do so much whose names won't be on a list of councilors at all. And these are people who handle the club library, who handle the club Lonerscope program, who edit the calendar, and who run these meetings from behind the scenes. And they all deserve a lot of credit. And I can't stress this enough, These hardworking volunteers do a lot to make all of this happen, but each and every member out there is encouraged to participate as much as you want, as much as you're comfortable with. Any member can be involved in the running of the club, not just the names on the screen right there. Any member can be involved in the running of the club and all of these great projects that happen. And I encourage you to do so. So that's great. Thanks so much for being able to for putting that up for me, Chris. I really appreciate that. So, before we wrap up, I've got one more door prize to give away. Oh my goodness! So, and wait, we need to get our random number generator back. We need to get that back. And we've got people here. So we have the National Geographic Space Atlas, another great big huge tome here. Spectacular images. It's absolutely a beautiful book. I can't say enough good things. And it is going to go out to magic number. And let's see who that is. 19 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Boy, you know, you can't get a more gripping meeting than watching me count, can you? That's pretty exciting stuff. Greg Emery. Greg, are you here with us? Greg, you're a door
Hey, John,
prize.
I'm here.
Hey, Greg, you're a door prize winner.
Excellent.
So fantastic. So same as the others who were with us earlier, who got their prizes earlier. Please feel free to get in touch. In the chat, I have put my club email for everyone. And of course, it's on the website as well. So excellent. So I think that, is there anything else left that I have omitted? Now is your chance, folks. So, all right, terrific. So we're going to wrap up the meeting. I want to offer my thanks to our guest speaker tonight, Lori Rousseau-Neptune, who just knocked it out of the park. That was fantastic. Matthew Mannering, who gave a wonderful edition of The Sky this month. Chris Stretch is doing all the behind the scenes work this month. A big thank you to Chris. All of you who have come out here, who've come out here to be with us tonight. I hope you enjoyed yourself. It's very nice to see you all in the Zoom format. I'm just going to say in parting, so I've been chair here for the past 3 years. It's been a wonderful, wonderful experience. They've been challenging years, I will say that. First, we lost our long time home at the Spectator building when the Spectator closed. And then we were forced to go online. We lost our new home when we went online with these Zoom meetings. And then, of course, we had to suspend so many of our programs due to COVID restrictions. So many of our activities were curtailed. These years were challenging for the club and not really what I was expecting when I signed on to be chair, not really what I signed up for when I took the job. But if I have one complaint about it all, I was really looking forward to the chance to be standing at the front of the room in front of all of you again in person and have the opportunity to welcome you back. And I regret that I'm going to miss out on that opportunity. But I do want to say that I am delighted that some of these programs are now getting back online. We're finding ways to do more and more of this stuff within the club. And I think it is a great testament to the club that we have come through these times stronger than ever. The club is doing just great. The membership is strong, it's active, and it is a testament to the membership of this club, meaning all of you, that the club is so strong. For the club really is the sum of its members. Those members, all of you folks, is what has made being chair so great. I get to welcome you. I get to introduce speakers. I get to host these meetings, but make no mistake, It is not the chair that makes all of this happen. It is the great members that pitch in, and I'm immensely grateful and appreciative to all of the members who have made my job so great over the past 3 years. So thank you all. And with that, we're going to wrap up the evening. It's been a wonderful evening. We will be back in November with our next meeting. Anybody can get in touch before then, and I look forward to seeing you all then in November. Thanks everyone for coming out, and good night, everybody.
Good night.